Hello viewers, in today's session we are going to discuss one important application of Euclid's division lemma, right? And here we have to prove that using Euclid's division lemma, that is the square of any positive integer cannot be expressed in the form of 5m plus 2 or 5m plus 3 for some positive integer m, right? So this statement can be proved using the concept of Euclid's division lemma, right? So before proving this statement, let us first quickly see the statement of Euclid's division lemma, and we'll see how using the concept of Euclid's division lemma, these type of problems can easily be proved. So let us start. So Euclid's division lemma states that for any two positive integers a and b, there exist unique whole numbers q and r such that a is equal to bq plus r, where the condition on r is given by r greater than or equal to 0 but less than b, right? So Euclid's division lemma says that for any two positive integers a and b, there exist unique whole numbers q and r such that a can be expressed as bq plus r and r is greater than or equal to 0 but less than b, right? And here r can take the value 0 and q can also take the value 0, right? And here this a is known as dividend, that is dividend, and b is known as the divisor, and q is known as the quotient, and r is the remainder, right? So in other words, we can say that when this b divides a, then the quotient is q and the remainder is r. So now when we divide a by b, then the quotient is q, and we have b times q, bq, and when we subtract, then we have a minus bq, and the remainder is given by r, so we have a is equal to bq plus r. So we'll use this statement to prove this statement, right? Okay, so now let us consider the positive integer as a. So let us consider the positive integer as a, and here we have to show that this positive integer, that is the square of this positive integer, it cannot be expressed in the form of 5m plus 2 or 5m plus 3. So we have to prove that a square cannot be equal to 5m plus 2, or a square cannot be equal to 5m plus 3 for some positive integer m. So now to prove this statement, let us take the value of b as 5, right? So we'll take b is equal to 5, and then this statement, that is a is equal to bq plus r, it becomes a is equal to 5q plus r, right? And the condition on this r is given by r greater than or equal to 0 but less than b. So we are taking now b as 5, so here we have 5. Now from this inequality we can conclude that r can take the value 0, 1, 2, 3 and 4, because r lies between 0 and 5, including 0 but excluding 5. So now we'll substitute r is equal to 0, 1, 2, 3 and 4 in this statement, right? So when we take r is equal to 0, then the positive integer a, it takes the form 5q plus 0, that is equal to 5q, right? And when we take r is equal to 1, then the positive integer a, it takes the form 5q plus 1. And when we take r is equal to 2, then a is 5q plus 2, and when r is 3, a is equal to 5q plus 3, and when r is 4, then a is equal to 5q plus 4, right? So what we have done here, we have considered a positive integer a, and we have to show that the square of this positive integer cannot take these two forms, that is 5m plus 2, 5m plus 3, right? So to prove this statement, we have taken the uh, help of Euclid's division lemma, and here we are taking b is equal to 5. So a becomes 5q plus r. The condition on r is greater than or equal to 0, less than b. So taking b is equal to 5. Here we have 5. So r can take the value 0, 1, 2, 3, 4. And then we have r is equal to 0. So substituting r is equal to 0, 1, 2, 3, 4, 1 by 1 in this equation. We have a is equal to 5q, a is equal to 5q plus 1, a is equal to 5q plus 2, a is equal to 5q plus 3, and a is equal to 5q plus 4, right? And here now we are interested in the square of this positive integer a. So now we are interested in the square of this positive integer, because here we have the square term. So now let us take the square of a. So we have a square is equal to 5q square. So this is 25q square. 25q square can be written as 5 times 5q square. Now see, 5q square is an integer, because q is an integer and q square is also an integer. So 5q square is an integer. So let us replace 5q square with some number, say m, that is a positive integer. So here we have 5m. So a square is equal to 5m. Now let us take the square of a. So here in this case, when r is equal to 1, we have a square is equal to 5q plus 1 square. Now this is a plus b square, so we have to make use of the identity a plus b square, that is a square plus 2ab plus b square, right? So here we have 25q square, 5q square, then we have 2ab term. So here we have 10q, and 1 square is 1, right? Now let us take these two terms, and let us take 5 common from these two terms. So we have 5q square plus 2q, and here we have 1. Right? Now 5q square plus 2q is again an integer, because 5q square is an integer and 2q is another integer. So the sum is again a positive integer. So 5q square plus 2q can be replaced by some other integer. Let us take it as m, right? So now we have here 5m plus 1. So viewers, here we are taking 5q square as m, and m is a positive integer, and here we have taken 5q square plus 2q is equal to m, where 5q square plus 2q is a positive integer, right? So in both the cases we are taking the same integer as a notation, that is m, right? So but if we wish to distinguish between the two integers, we can also take 5q square as m1, and here 5q square plus 2q may be taken as m2. right? So here we can take 5m1, and here we can take 5m2 plus 1, just for distinguishing between 5q square and 5q square plus 2q. So we'll follow the same rule for these r is equal to 2, r is equal to 3, and r is equal to 4. So now when we have r is equal to 2, we have a is equal to 5q plus 2. So let us take a square. So here we have 5q plus 2 square. Again, applying this identity, here we have 25q square. Then we have 20q, and here we have 4, right? Okay, so now here again we can combine these two terms, and we can take 5 common. So we have 5q square, and here we have 4q, and here we have 4, right? Now 5q square plus 4q may be taken as some another integer, that is m3. So we have 5m3 plus 4, right? And here m1, m2, m3 are denoting the positive integers, right? So let us take now r is equal to 3. So here we have a square and 5q plus 3 square. So this is 25q square. Then we have 2ab term, that is 2 times 5 times 3, that is 30q, and here we have 9, right? And see, here we have 25q square plus 30q. We can split this 9 in the form 5 plus 4, and now we can combine these three terms, right? So when we combine these three terms and we take 5 common, we have 5 times 5q square. Then here we have 6q, and then we have 1. 5 times 1 is 1, and here we have 4. So now we can denote 5q square, 5q square plus 6q plus 1 by some other integer, say m4. So here we have 5 times m4 plus 4. So now let us take this last case, r is equal to 4. So here taking a square, we have 5q plus 4 square, and again applying this identity, we have 25q square. Then we have here 40q 2ab, then we have here 16, right? So now we can split this 16 as 15 plus 1. So we have 25q square plus 40q plus 15 plus 1. So now we can combine these three terms. So now taking 5 common, we have 5 times 5q square plus 8q plus 3, and here we have 1. Now denoting this term, that is 5q square plus 8q plus 3 by some other integer, let us take it as m5, right? Because here see, q square is an integer, positive integer, 5 is integer, the product is integer. Similarly 8q is integer, 3 is integer, and the sum of these three integers is again an integer, right? So we have m5. So now we can write 5 times m5 plus 1. So viewers, from this discussion, we have seen that whenever we have a positive integer a and its square is denoted by a square, then this a square can take the forms using Euclid's division lemma as 5 times m1, and then we have 5 times m2 plus 1, then we have 5 times m3 plus 4, and then here we have 5 times m4 plus 4, and then here we have 5 times m5 plus 1. So now from these five forms, we can easily see that this one and this one are identical, and these two forms are also identical. So in a compact form, we can say that if we have a positive integer a and its square is denoted by a square, then a square can take the forms 5 times m1. The second one is 5 times m2 plus 1, and the third form can be taken as 5m3 plus 4, right? So a square can take the forms 5m1 and 5m2 plus 1, or 5m3 plus 4. So from this discussion, we have seen that the square of a positive integer a, that is a square, can be expressed as 5m, and 5m plus 1. A square can also be written as 5m plus 1, or a square is equal to 5m plus 4, right? So here m1, m2, m3 are some positive integers. So here we are replacing m1, m2, m3 by a single integer for notation, right? So we have a square is equal to 5m, or a square is equal to 5m plus 1, or a square is equal to 5m plus 4, where m is some positive integer. So now we can say that these forms, that is 5m, 5m plus 1 and 5m plus 4, are not of these forms, right? So we can now say that the square of any positive integer cannot be expressed in the form 5m plus 2 or 5m plus 3, but instead we can express the square of any positive integer in the form that is 5m, 5m plus 1, or 5m plus 4, where m is some positive integer. So now let us consider some examples. Now see the square of 5. So 5 square can be written as 25, and 25 can be written as 5 times 5. And if we take m as 5, so we have 5 times m, right? So a square, that is the square of any positive integer, can be expressed in terms of 5m, where m is some integer. Now similarly, when we take suppose 4 square, then we have 4 square is equal to 16. Now 16 can be written as 5 times 3, that is 15, plus 1, right? And here if we replace this 3 by m, we can write 5m plus 1. So 4 square can be written as 5m plus 1, and similarly in the third case we have 5m plus 4. So let us consider the square of 8. So 8 square is 64, and we can write 64 as 5 times 12, that is 60, plus 4. And this 12 can be replaced by m. So here we have 5m plus 4. So this is our this form, that is 5m plus 4, right? So in this case we have m is equal to 5. In this case we have m is equal to 3, and in this case we have m is equal to 12, right? So the square of any positive integer can be expressed only in terms of 5m, 5m plus 1, 6m plus 4, and we cannot express the square of any positive integer in these two forms, that is 5m plus 2 and or 5m plus 3.